15.1, and I think eventually assigned up through 16. Do you guys have any questions from that homeworks? Okay, that's fine. If you decide at a later date you've changed your mind and have something, we can always come circle back and get to that. So let's, I guess, get going then, huh? Section 15.2, we're going to talk about exponential and logistic modeling. So we're going to have a couple of specific models that we're going to work with in these in this chapter that we're going to have to be, or we're going to be specifically concerned with. So let's kind of jump on in here. So the first one is the exponential population model. Okay. So that model is P of t equals P naught times the quantity R plus, or 1 plus R over 100, all to the t. So the P naught is our initial population. R is the rate of change. That should typically be written as a percentage. And then T is time. Again, usually written in years. So let's look at an example. And as you might have guessed, with a title like modeling, the examples that we're going to look at are all going to be story problems. So I'm just going to drop these guys in out of the notes here. Make that a little bigger. All right, so we got a couple of examples here. we're asked to decide whether these are growth or decay, and then to find the constant rate of growth or decay. Basically, we're looking for is R, is what it's talking about. Okay. So to do this, you remember that for our exponential problems, everything we could write in the form of a times b to the x, right? Everybody agree with that? And what part of that tells us the growth or decay? We talked about this last week. You should remember.
B.
It's going to be the B. Okay, so which one's which? Grace. Oh. Yes. Growth. B needs to be bigger than 1. Well, there's no b's that are less than 0 based on our definition of an exponential, right? The b's have to be greater than 0 and not equal to 1. So those are our growth and decay. You okay there? Yes? Okay. So, if I take a look at part A, is this growth or decay? Okay. If I look at part B, is it growth or decay? So far, so good. Now, to figure out the R part, if I go back and I look at my exponential model, 1 plus R over 100 has got to equal B. Everybody's good there? So if I subtract 1 and then multiply by 100, I get 3.84%. We do the same thing for part B. If I subtract 1, I get negative 0.0133. If I multiply then by 100, I get negative 1.33%. Questions on that? Okay. Welcome back. All right, next example. says determine the population model with an initial value of 15, increasing at a constant rate of 6% every year. Okay, well, our population model, we said was this. So we have to fill in a value for P naught and for R. What's our value for P naught got to be?
Is that our initial value?
Yes. Good. And what's our value for R got to be then?
6%.
Yeah, the 6.
Are we writing it as 6 or like 0.06?
As a percentage. So the divide by 100 is there to take it out from a percentage. And if I just want to simplify that down, 1 plus 6 over 100 is 0.06. Okay with that? Do another example here. Mr. Kulik, didn't we already do this?
Yeah.
Close.
No.
What's different about this question from the previous one?
We have 6 months in the second instead of a year in the first.
Yeah. Okay. So what is that going to change? And we still have our model that we're using. What is going in for P naught?
When we keep that still at 15.
Yep. Okay. And what's going in for R?
Six.
Yep. Mr. Kulik, what am I going to do with that 6 months?
Is that where it goes for the T outside the parentheses?
Well, it's going to have to do with the T. Very good. Tyler?
Can you just multiply T by 2?
Yeah, that's exactly right. Why 2?
Because like the period is half of the usual one, so you have to double the time.
Because there's 2 compounds that happen in a year, right? Because 6 months goes into 1 year 2 times. Does that feel okay? So basically, you're getting double the growth. Does that feel okay? Okay. Let's do another. Oops. Drop another one in here. All right. Suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. Okay, well, this is a population growth situation, right? So we're going to start with our model. All right. The initial value would be what in this case?
120.
120. Yep, I agree. Okay. The R would be what in this case? Would not be 400,000. That would be cuckoo crazy.
Is 3 hours the time of the
3 hours is a time.
2 doubles.
Ah, so doubles is telling us our R, but R isn't equal to 2. Okay, so if you had 2 things and then it became 4 things, what percentage increase is that? Tyler?
100%.
100%, right? Because you have exactly twice as much as you had before, so 100% of your things have, or you've increased by 100%. Okay. What piece of information is still kind of hanging around there that we're going to have, or well, I guess there's a couple of pieces of information still hanging around that we have to deal with. Joe?
Well, for T, can we use something with 3 hours?
Yeah, so here we're going to have to make a little decision, right? So if we're measuring T in days, what would we replace the T with? How many times does 3 hours happen in one day?
8 times.
8 times. So you could replace the T with 8T if you wanted to measure this in days. I would probably measure it in hours though. So how many times does 3 hours occur in 1 hour?
0 times.
Well, 1/3, right?
You said 3 hours occurs in 1 hour.
Yeah, 1/3
Oh,
of
oh.
1/3 of that length happens
Okay.
in 1 hour, right?
Right.
Yeah. So I would probably write it this way and measure T in hours. But you didn't necessarily need to do it that way. You could have written it in days and still be okay. You just have to be cognizant of the unit that you're using there, right? Is everybody okay with that idea? Okay, now there's one other number that we haven't accounted for. What's that one other number? Yeah, the 400,000. So that's obviously got to be the future population, right? Everybody feel good on the setup here? Now, the question is asking us how long. So we're definitely solving for T, right? Everybody good with that? So to solve one of these equations where T is in the exponent, we learned last year that we could do this using a logarithm. We haven't talked about logarithms yet in this course for this chapter yet, so we're not going to do that. We're just going to do this graphically. So what I'm going to do is I'm going to plug in the left-hand side of my equation into y1 and the right-hand side of my equation into y2. Just FYI, I'm simplifying 1 plus 100 over 100 to just 2 because there was always less buttons to press. Wouldn't be wrong if you wrote it in as it's written there, but I just want to save my fingies. All right. Window. So let's start with the X's. This is going an hour. So in 2 hours, we'd have 240. In 3 hours, we'd have 240. In 6 hours, we'd have 480. In 9 hours, we'd have like 960. So it's going to be a while, right? Probably 100 hours is not a unfair estimate for an upper bound. Is everybody okay with that? I just kind of thought through like how fast is this going? Again, the X max, as long you just want to make it an overestimate, like it'll probably be way less than 100. The Y is talking about the population. So we're starting at 120. I think just 0 is fine. And we got to go up over 400,000. So I'm going to do 500,000. Oops. You stop moving around on me. Put that in the wrong spot. 500,000 goes here. And then maybe go by 50,000s. Okay. Hit graph. Let's take a look. There's my 400,000 line. Here's my curve. Woo! It's pretty steep. Doubling is really fast. Anyways, we're looking now for the intersection of these two. So second trace. And as we've mentioned before, we're going to use the intersect command. Since there's only two curves in one intersection, I can just press enter 3 times really quick. And it comes out with about 35.1 hours. Does everybody feel okay on these? No big deal, right? Very similar to the skills we developed last chapter. We're just applying it to some specific context here. The next situation that we want to talk about is radioactive decay. So those of you that have had a chemistry class recently, do you guys talk about radioactive decay? This would probably been a second semester topic. So if you're currently in one and haven't got there, that's maybe not so surprising. Okay. Anybody that's finished the chemistry class, do you guys talk about this in your chemistry course? Has anybody finished a chemistry class that's in here? Really? Nobody?
Oh, 2 years ago.
Yeah. You don't remember doing that though?
I don't know. It must have been over the point.
Well, like you could be that you didn't do it too, right? Like that's possible. I'm just curious.
No, we didn't talk about this. Sounds familiar.
Okay. Well, radioactive decay is the process in which a number of atoms for a radioactive substance change from a radioactive state to a non-radioactive state. Each element on the periodic table does this in a fixed amount per given unit of time. The half-life of a radioactive substance is the time that it takes for exactly half of a radioactive substance to become non-radioactive. So half-life is implying that the R value in our population model is going to be what? Well, since it's decay, what do we know right away about the value for R?
Less than 1.
It's negative. Right? That way, when we add it to 1, we're going to get a number that's less than 1. Everybody's okay with that? And half of the stuff goes away in that amount of time would imply the percentage is if you had $4 and then an hour later you had $2, half of that,
Negative 100%. No.
not negative 100%. That would mean you'd have $0. 50. Yeah, negative 50%. Very good. Everybody's okay with that? All right. So let's look at an example. Again, we're still using this same population population model. We're just using it in a different context. The big takeaway, though, here for these radioactive decay problems is that the R value won't actually be given in the problem, but as soon as you hear the phrase half-life, you know that the R is negative 50%. Okay? All right, so suppose that a half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be only 1 gram remaining. Okay, let's start piecing this together. What's our P naught? The initial amount. 10 grams. Yes, sir. And what's our R?
Is that 150 coming from the negative 50?
Yeah, since we have the word half-life in here. R is going to be negative 50%, so negative 50 over 100. Yes?
So when you see halfway, you always write negative 50?
Yes.
Okay.
You're welcome. 35 days. What are we doing with this? Yeah, that's how we're gonna alter our time. So the question becomes, how do you want to measure this problem? I would probably want it to make this in the t in days, since this is the half-life is measured in days also. So how often does 35 days occur in 1 day? 1/35. So I'll make that t over 35. Is that okay? So this is in days. And there's one piece of information left that we haven't talked about. It wants to know the time it would take for there to be only 1 gram remaining. What is that 1 gram? That's that future population. And what's the story now? It's calculator time. Left-hand side into Y1. Right-hand side into Y2. Again, I'm simplifying and writing this as 0.5. Note that that's the same thing as 1 plus negative 50 over 100. I just want to save my fingies from all the button pushing, but it certainly wouldn't be wrong to write it exactly as it looks on our sheet of paper. And then I have x to the, then I have to the x over 35 power. Let's reset our window. So our x's are representing the days. After 35 days, I'm going to have 5. After 70 days, I'd have like 2.5. After 105 days, I'd have like 1.25. So it's definitely going to be over 100. So maybe I'll bump that out to 200. Everybody's cool with that? You get my rational, how I was able to kind of reason that out quickly. Okay. The minimum value that this could have, since its decay is 0, right? You can't get less than 0 stuffs left. Everybody cool with that? And our initial amount of stuff is the most stuff we're ever going to have, so that was just 10. So that looks pretty good. Let's go ahead and hit our graph. There's our 1 line. There's our decay curve. Whoop! There's our intersection we're interested in. To find that intersection, second, trace, intersect, enter, enter, enter. 116.3-ish. And this is days because that's what we decided the time unit was going to be. Everybody cool with that? Okay. All right. Remember last time we talked about how logistic growth or decay can be kind of more realistic model to use, particularly for population situations where it's like, yeah, you're just not going to get like population growing unbounded because eventually you just run out of space or resources or whatever, right? You guys kind of remember we talked about that last time? So let's look at doing the same kind of problem here, but using a logistic model instead. So you'll notice here, we've given you that logistic model in the problem. You're not being asked to build that on your own. But we're asking you some interesting questions here. So how many bunnies do you have initially?
No, 99.
Well, that would be the amount of bunnies you have at time 0, right? Time 0 would be the initial amount, right? So all I'm going to do is plug 0 in for t. So 0.5 or negative 0.5 times 0 is
0.
E to the 0 is
0.
no
1.
1. 1 times 99 is plus 100 plus 1 is, so we have 8 bunnies. Again, you could have typed that all into your calculator, but it was good mental math review there, right? Joe.
Okay. The E, does that, what is that? That represents like 10.
That's a number.
Yeah,
That number is 2.718, yada, 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 yada. That's that
Oh.
irrational number E. That's different than on your calculator. You have the capital E button, which is scientific notation.
Okay. Cool.
Yep.
Thank you.
Yeah, no problem. So part B asks, what is the maximum sustainable population of bunnies on our farm? Somebody said the answer to this question already. 800 is the answer. Why? So recall for logistic growth, we have two asymptotes, or for all logistic functions, I guess. You have an asymptote at y equals 0, and you have another at y equals c, where that c is the numerator of our logistic function. So that's the upper bound that our logistic curve can have, is that other one. So it'll always be the numerator is the upper bound. Does that feel okay?
Yes, sir.
Okay. And then C, how long will it take to have 500 bunnies? How long is asking us to solve for time. So I'll plug 500 bunnies into B of t. And we're just going to go back to our calculator. Boy, this is feeling a familiar skill, isn't it? Again, I'm going to use the fraction command here. So alpha y equals, and then pick the first option. So I don't have to mess around with, with too many of those silly exponents or parentheses. Remember how to get the e to the button is, or if I want e on my calculator, I press second and then the LN button. The LN button is on the left-hand side. Couple up from the on. It automatically prompts you to put an exponent there with it. So 0 is a good minimum time. A maximum time, I have no idea. So I don't know, let's pick 50 or something. I'm just guessing. We can always go back and change it. The Y min should be 0. The Y max should be 800. Go by hundreds there, seems reasonable. Let's go. There's my 500 bunnies. There's my logistic curve. Boy, that shot up to the carrying capacity pretty darn quickly. So they're just looking at the intersection there. So second, trace, intersect, enter, enter, enter. And I got about 10.2 years. Is it years? What was the 10.2 times? What was time in? Oh, yeah, measured in years. Okay. So years. Well, that makes it a little less. I was like, jeepers creepers, those bunnies are reproducing like crazy. But 10 years is a lot less crazy. I didn't know 10 once, right? Is that 10 minutes? Jeez, old Pete's bunnies. Take a break, you know? Ha ha ha. All right. Where are we at time-wise? Let's stop here. This feels like a good place to stop before getting to the next section, which is a biggie. So a couple of things here before I sign off for you guys. Just as a heads up, seniors, you guys are heading towards the finish line here. I'm going to put in the drops over spring break. Unfortunately, when I put in the drops, I can't put them in just for the seniors. I have to do it for everybody. So everyone else, you're going to see your grades move a little bit when I put in the drops. Now keep in mind, when I put the drops in, when you look at your grade book, you can't tell what the computer's dropping you. I promise you it's doing it correctly. those of you that are juniors that are going to continue on doing things after the seniors leave, I promise you that as new grades come in, the computer automatically updates what it's dropping. So if a new low score pops in, it'll automatically like switch what it's dropping to include the new low score. I promise you that's working. But you're not going to see another big grade jump at the end because we're doing the drops now when the seniors are leaving. Seniors, when we get back from spring break, I'll have an exam study guide stuff for you, an exam info for you, and we can make a decision about whether you want to take a doubled high test score or a drop or a retake. Everybody else, juniors, will wait and make that decision for you guys until we've taken all the tests. Seniors, does that sound okay? Good plan? Yes, sir?
Everything sounds good, but are seniors having a test on this unit?
We'll just play it by ear.
Okay, cool.
If we don't finish it before spring break, which doesn't seem likely, it'll probably be exam only content. Would be probably the way I would play it. I probably wouldn't try to give you a test that week we come back from spring break, because that seems like just put on the exam and we can study for the exam, and just
Right.
like
Okay, that sounds good.
seems easier on everybody, so you're not studying twice. You know, you probably have a lot going on that last week of school anyways. Yes, Emilio.
So are you doubling the highest test grade and dropping the lowest score, or is it just one?
So the policy is you can retake a test or you can take a doubled high test score. The retake is capped at 80%. The drops would apply to homework and homework quizzes. That's where we have drops at. Okie doke. Okay.